Welcome back to the Quantum Rings Quantum Summer School. In the last 2 weeks, we talked about some foundational building blocks of quantum algorithms, like oracles and amplitude amplification, and we also learned about some small toy algorithms. Today, we're going to put all of that together and talk about Grover's search algorithm, which is an algorithm for searching through an unsorted list. It provides a quadratic speedup over the best classical approach. Let's get into it. So today we're going to start off by talking about the phase flip oracle and amplitude amplification. We learned about these a bit when we talked about the building blocks of quantum algorithms, so we're going to go over those again today, and then we're going to put those together to create Grover's search algorithm. Let's start by reviewing the phase flip oracle. So the phase flip oracle flips the phase of a target state. And in order to create the phase flip oracle, we can leverage the controlled Z gate. And we know that the controlled Z gate flips the phase of the 1-1 state. So in the 2-qubit case, if we have 0-0 in, we'll get 0-0 out. If we have 0-1 in, we'll get 0-1 out. Same for 1-0. And finally, for the state 1-1, we'll get the same thing back, but with a phase flip. And one important thing I want to note here is that we often draw the controlled Z gate with just 2 dots like this, and it's symmetric. So it doesn't matter which one is the control and which one is the target, because it has the same action either way. So if we want to turn this into a phase flip gate, for example, for the target state 1-0, we want to turn the state 1-0 into the 1-1 state. Then we can apply the controlled Z gate, which will flip the phase of the 1-1 state. And then we want to revert back to the original state. So for this one, we have the state 1-0 that we want to flip. And just as a reminder, the least significant bit will be Q0, and then it goes up from there. So in this case, we'll want to first apply an X gate to Q0. So then at this point in the circuit, we'll be in the state 1-1. Now we can apply a controlled Z. And finally, we need to apply another X gate to send us back to the original state. So this is a phase flip oracle for the target state 1-0. And we can pretty easily extend this to more qubits. So if we wanted to do the 4-qubit case, for instance, for the state 0-1-0-0, again, this would be the most significant bit, and this would be the least significant bit. For this one, now we want to apply an X gate everywhere where there's a 0 in our target state, so here, here, and here. And then now we'll be in the all 1 state, so we want to apply a controlled Z on all of these, which will leave any state but the all 1 state unchanged. And then finally at the end, we want to apply our X gates again. We can visualize the action of the phase flip oracle. So if we have our target state being called W, we can create kind of an orthonormal basis by also considering V, which is everything but W. So we can write this out as 1/n minus 1. And it's the sum of all bit strings of length n, which are not W. So then, if we have some arbitrary state psi, and we want to know the action of our phase flip oracle, which is a unitary operation, then what's going to happen is it's going to flip the sign of the W state only, and everything in V is going to be unchanged. So essentially, this component is going to get flipped. So basically, the action of the phase flip oracle is to flip us over the state V. So once we've been able to achieve a phase flip, the next thing that we would want to do is amplify the amplitude of the correct state. So we know that our measurement in a quantum computer is going to be probabilistic. So there'll be some chance that we'll measure the correct answer. We want to make that chance as high as possible. So the diffusion operator gives us a way to amplify the amplitude of the correct state. And we do this by inversion around the mean. And just to get a sense of this with the real numbers, if you had some collection of numbers x1 through xn, you could find the mean, which is just the average of all of them. And then if we were to look on a number line, the mean is going to be some distance away from your number of choice, which we'll call x. And then we want to know what we get when we invert around the mean. And that would be also equidistant. So in this case, we can write down x prime equals x minus 2 of these, so 2x minus m, which is just 2m minus x. And we can extend this same approach to a quantum computation. And so the unitary operator for our diffusion operator is just going to look like this. It's going to be 2, and then this is the outer product of a state S minus the identity. And S is just the equal superposition state. So it's an equal linear superposition of all the bit strings of length n. We can think about the action of this operator on an arbitrary state psi. So first, just to make this a little bit easier for ourselves, we can re-express psi in a more convenient way. So psi has some S component. So there's some component of psi that is along S. And then there's some component of psi that is everything that is not S. So just to emphasize again, psi has a S component and an everything but S component. So the inner product of S and Y would be 0. So now consider the action of our diffusion operator on psi. So this is going to be 2s acting on psi minus psi. That's from the identity. And we know that the inner product of S and psi is alpha. That's this coefficient here. So now we can write this out as 2 alpha s minus psi, which is alpha s, plus beta y. And this is just alpha s minus beta y. So basically what's happening here is that the non-S component gets a phase flip. We can visualize this as follows. So we know that we have our target state W and we have our everything else state V, and we can also plot S on these axes as well. So S is the equal superposition of all states, which includes V and includes W. But V is everything except W, and W is just itself. So S has a lot more overlap with V than it does with W. So S is going to lie closer to the V axis than the W axis. And if we start with some state psi down here, and we apply the diffusion operator, basically what's going to happen is the component of psi that's not along the S axis is going to get flipped. So we're going to get mirrored over the S axis. Okay, so now we can see why this might be useful, because let's say we want to measure the target state W, and we had this psi beforehand, and then we apply the diffusion operator, which inverts psi over S. Now we can see that the overlap of W with our state has greatly increased, and the overlap of our state with V has greatly decreased. So this means it's going to be more likely for us to measure W than not W, which is what we want. So how do we go about constructing D? Well, first we should start off a little simpler. So let's consider this instead, where instead of having S here, I've replaced it with the all zero state. And just remember that this is a shorthand notation, so 0 to the n is really just 0, tensor 0. Or you could also just write it as like a bunch of zeros. It's the all zero state, basically. So we know that the diffusion operator, which is 2 times the outer product of S minus I, is going to flip the phase around S. So this is going to flip the phase of everything but the all zero state, which is equivalent to saying flip the phase of only the all zero state. Again, just emphasizing the reason for this is because we don't care about the overall global phase. We only care about phases relative to each other, so it doesn't actually make any practical difference if we flip the phase of just the zero state or we flip the phase of everything but the zero state. So what does this sound like if we flip the phase of only the zero state? This sounds like a phase flip oracle with the target state being the all zero state. So we can construct this pretty easily for any number of qubits. For example, with 4 qubits, we have zeros in all locations. So we should apply an X gate on all the qubits, then we have our multi-controlled C, and then X gates on all the qubits again. But our full operator actually has the outer product of S here, rather than the zero state. So all we have to do here is just recognize that the S state is the equal superposition state. And the way that we create that is applying a Hadamard gate to the all zero state. Or basically we prepare every qubit in the zero state and then apply a Hadamard to each one. That puts us into an equal superposition of all bit strings of length n. So then we can recognize that if we take our operator, which is a phase flip oracle for the all zero state, and then we pre and post multiply it by Hadamards on all the qubits, then those Hadamards are going to combine with the zeros to make S's, and we know that a Hadamard is its own inverse, so the second part will cancel out to be the identity as well. So now we can see what the full operator would look like. All we have to do is just take our phase flip oracle for the all zero state and sandwich it in between Hadamards on all qubits. So now we have all pieces of the puzzle that we need to create Grover's search algorithm. But first, let's talk about the problem statement. So the problem at hand is searching through a list for a particular item. So just imagine that you have some list or database and you want to find some particular entry. Now, classically, how would we go about doing this? Well, there's kind of 2 situations that we can consider. So one would be a sorted list. So for instance, we could have something like this. So this would be an example of a sorted list. And let's say we're looking for the item 27. Well, the most efficient thing that we could do is we could start by looking at the middle number. So we look at the middle number and we say, okay, is the number that we're looking for bigger or smaller than the current number? We say, okay, 27 is smaller than 161, so we know that this whole half of the list we don't even need to look at. Then we can look at the middle of what's left, which is 3, and we say, okay, is 27 bigger or smaller than 3? It's bigger, so we know that everything here is we don't need to look at anymore. And then finally we keep doing this until we find our number of choice. So this is called binary search. And I gave it as an example numbers, but you could also imagine if it was some other sort of organization, like if it's an alphabetized list or by date or something like that. So how long would this kind of binary search take? Well, each time you query or look at an item in the list, you're gonna cut out half of the possible entries. So basically, we want to know how many times can we divide our list of length n by 2 until we only have one thing left. And that's going to be basically log base 2 of n. So binary search is going to take on the order of log base 2 of n. What if the list is unsorted? Then there's really nothing we can do. The best thing we can do is just go one item at a time and say, is this what I'm looking for? Yes or no? Is this what I'm looking for? Yes or no? And basically this is just going to be order n, because in the worst case scenario, we may have to look at every single item in the list. So now let's see how Grover's search algorithm can speed this up and give us better than order n for searching through an unsorted list. So here is Grover's algorithm. It has all the pieces that we're already quite familiar with. So the first thing that we're going to do is we apply a Hadamard to every single qubit, and that puts us in the equal superposition state. So then at this point in the circuit, we would be in that state S. Then we're going to apply the phase flip oracle, which is going to flip the phase of our target state. And then we'll apply the diffusion operator, which flips all the amplitudes over the mean. And depending on the situation at hand, we may want to do this more than once. So we can also take this part, and we may want to do this, let's say, n times. And we're going to talk in a little bit about how you would determine this optimal number of iterations. And then, of course, at the end, we're going to measure all the qubits. But first, let's think about how we would visualize this. So let's go back to our graph, which has two axes, the W axis and the V axis, which is everything that's not W. And the very first state that we're starting in is the S state, because we just applied Hadamard to all the qubits. So this is where we are at the first step. Then we're going to apply the phase flip oracle, and this is going to flip the phase of the W component only. So this is going to be after the phase flip oracle. Then we're going to apply the diffusion operator, and that's going to flip us over the mean, which is S. And so that will send us up to here. And that's our third step. And now we can see, after we've done all of these steps, our state that we've ended up in, which is this third one here, the overlap with the W state has increased, and the overlap with the V state, which is everything that is not W, has decreased. And this is exactly what we want, because we know that if we measure our qubits now, we're going to be more likely to measure the W state, at least than we were in the beginning. And now the question is, how many times should we do this so that we have a maximum likelihood of measuring the W state? Okay, so the way that we first start off is in this configuration, and there's some angle between the state S and the state V. And this angle is going to be given by the overlap between the S state and the W state. So actually, sine of this angle, theta, is going to be the magnitude of the overlap between S and W, which is just going to be 1 over root n. And I just want to point out here that the length of the hypotenuse would be 1, so I'm kind of neglecting that here. And then if we consider the case where n is pretty large, then S is going to get closer and closer to V, so theta is going to get pretty small. And in that limit, where theta is much less than 1 radian, we can say that theta is approximately just 1 over root n. And this is just coming from a Taylor expansion. So now we can see what's going to happen after we go through one iteration. So first we would apply our phase flip oracle, and that would flip us down to minus theta. And then we'd apply our diffusion operator, which would flip us over to S. And this angle here would be 2 theta. So now after one iteration, we've gone from theta now to 3 theta. Just filling this out. We started off at theta, and then we're at 3 theta. And if we were to do this again, so now we apply the phase flip oracle, that would send us down to here, which would be minus 3 theta. And then if we flip over S again, then this angle would be 5 theta. And if you keep doing this, what will end up happening is it will just keep going up by 2 theta. So after n iterations, the angle will be 2n plus 1 times theta. And what do we want? We want the angle to be as close to pi over 2 as possible. So we want 2n plus 1 times theta to be pi over 2. So we know that theta is around 1 over root n. So if we just plug all that in, we would get that n equals 1/2 times pi over 2 root n minus 1. And since we would expect n to be big, then this is approximately pi over 4 times root n. So I just want to emphasize here that this algorithm is going to require order root n queries. Classically, we saw that for an unsorted list with linear search, the best that we can do is order n, and here we've shown we can do it in order root n. I want to emphasize a really subtle point here. You may have some hesitations about this because, for instance, we provided the oracle, and to construct the oracle, we already needed to know the state that we were looking for. So wasn't this cheating? Didn't we already have the answer before we even looked? And the answer is yes, if you think about it that way, but that's not really the heart of the problem here. So really the problem at hand is that we have some function f of x, and this f of x outputs 1 if x is equal to w, and it outputs 0 otherwise. And our goal is to find w. So in the case classically, when we're looking through our list, we're saying, oh, is this the item I'm looking for, yes or no? A yes would be 1 and a no would be 0. And there's only one answer that would output 1. Now in this case, the oracle is our way of querying, is this the item I'm looking for, yes or no? So in that sense, we aren't cheating, and the algorithm is working as intended. Now let's move over to the coding notebook. First, run the first cell to import all the libraries that we need. And then let's talk about the phase flip oracle. So we know that the phase flip oracle flips the phase of our target state. And in terms of coding this up, we've encountered before the controlled X gate and double controlled X gate, which is the Toffoli gate. You can do the same thing with the Z gate. So we have like CZ or CCZ. I'm looking at this. These are commands that we've encountered before, but now we're going to potentially have many controls. So if, for instance, if we had 4 qubits, we would have triple controlled Z gate, which we need for our phase flip oracle. So in order to do that, we're going to use a multi-controlled multi-target gate. And the way that we would do that is the gate itself can be written in this way. So it's multi-controlled multi-target. And the first argument is going to be the gate that we want. So in this case, it's going to be the Z gate. The second argument is going to be the number of control qubits. So for us, let's have it be the number of qubits minus 1. And then the number of target qubits, which in this case can be 1. And this itself is just a gate. We want to put this into our quantum circuit, so we're going to use the compose function. And then we also have to use this argument in place to say that we want it to modify the circuit in place rather than returning a new circuit. So here's what this would look like. So here we have 4 qubits. We have our multi-controlled Z gate with 3 controls and 1 target. So now let's practice constructing the phase flip oracle for an arbitrary target state. So let's say our target state is 0, 0, 1, 0. The number of qubits is going to be the length of the target state. And then let's walk through the steps here. So first, we want to flip the bit string to match the Qiskit bit ordering. So this is going to be our target state, but we want to do it in reverse. Then we want to find the indices of everywhere where there's a 0 in our bit string. So we can do this as a list comprehension, or you could do it as a for loop if you like. So it's going to be any index I in the range of the number of qubits if that element in the reverse string is equal to 0. Then we want to apply an X gate at every 0 location. So if there are any, because otherwise it will throw an error, then we want to apply an X gate on those indices. Then we want our multi-controlled Z gate. So we can compose that. And finally, we want to apply an X gate at every 0 location again. So that's the same as this. So let's see our phase flip oracle. Oops, run the first cell first. And again, I forgot to say in place equals true, so it didn't modify my circuit object. So now this should work. Okay. So here's our phase flip oracle for an arbitrary target state. So here I had 0, 0, 1, 0, but we can make it whatever we want. And then we can wrap this up into a nice function that we can use later. So I'm just going to grab all of this and put it into this Grover oracle function. And basically we're building up a small quantum circuit which has the oracle in it, and then we're going to return that quantum circuit. And we're going to use the compose function later to put this mini quantum circuit into a bigger quantum circuit. So now if you want to challenge, can you build the Grover oracle for 2 target bit strings? So the way that this would work is it should apply a phase flip to each target string. So for instance, if you were targeting both the 0, 0, 0 state and 0, 1, 0, it should flip the phase of those 2 and not of any of the others. So now let's take a look at amplitude amplification. So for this one, we know that it's going to be the phase flip oracle for the all 0 state, sandwiched with all Hadamards on both sides. So we can start off picking a target state. We can put our system into the full equal superposition state. And then we want to apply our phase flip oracle. So our oracle this is our function that we just defined above, Grover oracle for our target state. And then when we do this qc.compose, we're taking this quantum circuit and we're mapping it onto a different quantum circuit. And remember, we need this in order to actually modify the quantum circuit object. And then we want to apply our diffusion operator. So the first thing we need to do is apply Hadamard to everything. Oops. Then we need to apply an X gate to everything. Finally, we can apply, we want to apply our multi-controlled multi-target Z-gate. And then we gotta do the same on the other side. So apply X to everything and apply a hat mark to everything. And make sure that you run your cells. So here we have our Grover oracle and our target state. Okay. So here's everything that we've got. We first create our equal superposition state. Then we have our phase slip oracle. Here we have our diffusion operator. And then finally we measure everything. So so we can use it again later, let's grab our diffusion operator and turn that into a function as well. We can, just to make it easier on ourselves, define a quantum register first, and then build our quantum circuit out of that quantum register. Okay, and then we can put everything together. So all of this is the same as before, but now we can also grab our diffusion operator and add that into our circuit as well. So this should turn out the same. And now we can actually run this and see what result we get. Okay, so we can actually see that we measured the 0, 1, 0 state 805 out of 1,000 times, and the other states we measured some of the time, but not that much. Overwhelmingly, we measured the state that we wanted to measure. So you can see that this is working. We had the phase slip oracle to flip the phase of the target state, and then the diffusion operator flips us over the mean, which greatly enhances the probability of measuring the state that we want. So now let's put it all together into the full algorithm. So the first thing that we can do is make Grover's algorithm from scratch. And we already have all the parts. We built our phase slip oracle for an arbitrary target state, and we also built our diffusion operator for an arbitrary number of qubits. So the first thing that we'll want to do is tell our target state. The number of qubits is the length of our target state. We have our oracle and our diffusion operator. These are the functions that we just defined. And then we need to know the number of iterations that we want to go for. So we know that the optimal value should be approximately pi over 4 times the square root of the number of qubits. Oh yeah, the number of bit strings. So that should be 2 to the number of qubits. And we want to round this because this might not be an integer. So for instance, if the target state has 3 qubits, then the optimal number of iterations would be 2. So here we can make our quantum circuit with a quantum and classical register. We apply a Hadamard to everything to create the equal superposition state. And then we need to loop through the number of iterations that we want to do. And the first thing we can do is apply our oracle. And then we want to also apply our diffusion operator. And then after we've done the optimal number of iterations, we want to measure. So let's do this 1,000 times. And we can see that we measured the state that we wanted to measure 942 out of 1,000 times. And the other ones, a very small percentage of the time. So one thing that we could ask is what happens if you overshoot the optimal number of iterations? So let's consider that case. I'm grabbing the same things from over here, but now we want to overshoot the number of iterations. So it said the optimal number of iterations was 2. What happens if we do 3? So now we can see that we've actually overshot. And if you think about the angles that we were talking about before, the angle of our state has passed pi over 2. And so now the overlap with the W state, our desired state, is actually decreasing again. And if we did even more, then now you can see that we've actually had the opposite effect of what we want, where our target state has a lower probability amplitude than the rest of the states. And we can keep doing this, and eventually we'll come back around again. So what's happening here is we've actually gone around the circle a full time, and we're back up near pi over 2 again. Another thing that I'd like to point out is that we can also do more qubits. So maybe we want to do a 6 qubit state, then the optimal number of iterations would be 6. And here we can see that this works super well. We measured the state we were looking for all but 2 times out of 1,000. So I would encourage you to play around with this, try out different marked strings, different number of qubits, different number of iterations. Another thing that's really useful is we don't have to build everything from scratch. So for instance, Qiskit has a lot of pre-built things that we can use, and we can very easily transpile them so we can run them on Quantum Ring backend. So here's an example. So same thing as before. I'm just going to grab the optimal number of iterations from up here. But now we have to use the same oracle that we already built, but now we can use a built-in Qiskit circuit called Grover Operator, and all we have to do for that is provide the oracle. And then we can just use that Grover Operator instead. And then we need to transpile this so that we can run it on the Quantum Rings backend. So the way that you do this is you just specify the backend and the provider and the number of qubits, and then you can use this function transpile. And if we look at this, it actually looks super different from what we've seen before when we built it from scratch. And that's just because the transpiling process maps it into a certain gate set. And we know that there's certain universal gate sets, so the one that's being used here has different gates than what we were working with directly. So the transpiler just does this mapping for you so that it's ready to run on the Quantum Rings backend. This is really nice because it allows us to access all the tools that Qiskit has to offer while still being able to use Quantum Rings. And now we can execute this by using a sampler. So this is a little bit different than how we've been running things before. Just another way to run simulations. So we have the sampler and we can run this for a given circuit. And then we have some quasi distribution that we get out of this. So if you'll notice, now we're not talking about any specific number of shots, but rather the sampler is going to tell us the probability amplitudes of each of the states. So if you'd like an extra challenge, you can try and modify our algorithm so that you can search for 2 target strings. And so all you need for that is you need to modify the phase flip oracle to flip the phase of 2 strings, the 2 target strings. And then everything else works the same. So the amplitude amplification process would still flip everything over the mean, which would amplify both of those states. And then once you have that built, some things you can consider is how many shots would you need to perform in order to be convinced that you found the 2 target strings? And then how does the optimal number of Grover iterations change? Today, we built Grover's algorithm from scratch, and we saw how it can provide a quadratic speedup over the best classical approach when searching through an unsorted list. Next week, we're going to learn about the quantum Fourier transform, and the week after that, we're going to learn Shor's algorithm for prime factorization. I'll see you next time.